Welcome to Mastering Solutions. This question, the actual math to get the answer when we plug everything at the end is not too bad. It just takes a little bit of algebra for us to get there. So I'd like to start on this one with the equations that we're going to be using, because what we need to find is the minimum and maximum values of the sarcomere length. Now, what do they mean when they say that? Because some psycho person let them cut their freaking forearm open and then let a researcher shine a laser through the muscle and measure the light as they flex their muscle while they're doing that. So the sarcomere is the distance between the muscle fibers, right? That's what they're talking up here. And that is acting as the diffraction grating here. This is D. That's what we need to find, is what is the value of the widths of the sarcomeres that the light was going through, diffracting the light. So we're going to use y is equal to L tangent of theta, but we don't have D in there, and that's what we need, right? So we're going to have to use some other equations as well. We're going to use sine of theta is equal to m lambda over d. Now we've done this in several of the other equations. Theta is equal to inverse sine of m lambda over d. Then we'll plug this in over here, and then we have to rearrange all that to solve for d. And that's where some of the algebra comes in. So first let's plug it in, then we'll go on to the next step. So y is equal to L tangent of inverse sine of m lambda over d. So now to isolate the d, first let's divide both sides of the equation by L. So if we go by L, that'll cancel. I'm going to do a different color. Okay, so now we'll have y divided by L is equal to tangent inverse sine m lambda over d. Now we can take the inverse sine of both sides. And so when we come up here, we'll have inverse tangent of y over L is equal to inverse sine of m lambda over d. Okay, now the next step that we'll do is let's take the sine of both sides, right? So now we have sine times the inverse tangent of y over L equals m lambda over d. And then now we can multiply both sides by d, and then we'll divide this back over. So we'll have d times all of this. I just don't want to rewrite it again. And then we'll divide that over here to the other side. So d is equal to m times lambda all divided by sine times the inverse tangent of y over L. 2 and there. Okay, so we made it. This is the final equation to solve for d. And now we're going to have to plug in two values. There's one last tricky little bit here where you could get messed up. They say that the M2 fringes on either side of the central maximum are these two lengths. But that's going to be y right here, but y is not between the two central maximums. If we had our central max here and M1 and M1, or I guess they say M2, so we'll do M2, M2, the y is from the central max out to 1, but they say they measured from the central max to the central max. So we need to take this number and divide it by 2 for our y value here. So let's give us some more room and let's do these ones. So let's start with the minimum. So d min is going to be m is 2. There, so we can see our equation. Okay, so m2. And then they say that the wavelength that we're using is the 632 nanometers. And then we're going to divide all that by sine times the inverse tangent. And then here is where we need to take the first number, the 2.7 centimeters, and we need to divide that by 2. So we're going to have 1.35 times 10 to the negative 2 for centimeters. And then that's all divided by L, which they tell us is 2.4 centimeters, which is 10 to the negative 2. All right, so now we can plug all this in. And let's write the maximum too, so we can just do them both at the same time. So we have 632 times 10 to the negative 9 meters, all divided by sine, inverse tangent. And then this time we're going to take the other one, the 1.9, which will be 0.95 times 10 to the negative 2 meters divided by L, which is the same as 2.4 times 10 to the negative 2 meters. All right. So now when we plug these in, we'll have 2, let's do parentheses. Okay, so 2 times 632 times 10 to the negative 9 meters. And then that's divided by sine times inverse tangent times 1.35 times 10 to the negative 2 in this case, divided by 2.4 times 10 to the negative 2. And then that gives us 1, 2, 3, 4, 5, 6. So 2.6 times 10 to the negative 6 meters. And that is another way of saying 2.6 microns. So that's the answer for our minimum. And then we can plug the same thing in here and just change our value to give us the maximum. So instead of 1.35, we're going to have 0.95. And that's going to give us 3.4 times 10 to the negative 6 meters, which of course is 3.4 microns. So that is the value for D at the minimum and the maximum as the muscle fiber is contracting while the psycho shines a laser through your open freaking arm.